The scale of what's needed for this is so daunting that we need every single one of these clean technologies to be unbelievably successful, and then we might just make it.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues. Hello and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. Welcome. Energy-dense fossil fuels have provided abundant energy for the industrialization of human civilization for hundreds of years. Now, we need to deal urgently with the impacts of this success. Progress is being made in identifying alternatives to electricity production and electrification of transportation. However, this is not the whole problem. Roughly 1/3 of fossil fuels are burned in high-temperature industrial materials processing, and these cannot be easily replaced with electricity. Unless we find a way to replace coal burning in the production of steel and other materials, climate change will continue to accelerate. One option for achieving the deep decarbonization we need is to burn hydrogen. Today I have the honor to welcome the co-founders of TerraPraxis, Kirsty Gogan and Eric Ingersoll. TerraPraxis is a nonprofit organization focused on action for climate and prosperity. Kirsty Gogan has more than 15 years' experience as a senior advisor to government on climate and energy policy. Kirsty is managing partner of LucidCatalyst, an international consultancy focused on multiplying and accelerating zero-carbon technology options available for large-scale, affordable, market-based decarbonization of the global economy. Kirsty chairs the UK government's Nuclear Innovation Research and Advisory Board Cost Reduction Working Group. Kirsty also co-founded Energy for Humanity, an environmental NGO focused on large-scale, deep decarbonization and energy access. Ms. Gogan, welcome to The Rational View.
Thanks, Al. It's great to be here.
Thank you for coming on. Eric Ingersoll is a strategic advisor and entrepreneur with deep experience in the commercialization of new energy technologies, renewables, energy storage, oil and gas, and nuclear, with a special emphasis on advanced nuclear technologies. Eric develops commercial strategies for advanced energy technologies. Eric co-founded NGO Energy Options Network, a group of technical experts working to accelerate the commercialization and deployment of alternative climate mitigation options. Eric was a member of the Renewable Energy Advisory Group of the National Commission on Energy Policy and was honored at the Obama White House as a champion of change in renewable energy. Mr. Ingersoll, welcome to The Rational View.
Thank you.
Kirsty, you must be very busy managing all of these organizations. Why did you decide to set up TerraPraxis?
Well, I started out as sort of, by default, anti-nuclear as an environmentalist. And the more I learned about nuclear energy, the more I realized that firstly, almost everything I thought I knew was wrong. And secondly, that actually nuclear energy could be a really important part of our climate toolkit. Alongside wind and solar, and that actually our chances of getting all the way to zero could be, improved greatly if we were to sort of apply the same creativity and determination to nuclear energy as we have done really successfully for wind and solar. So I started Energy for Humanity to advocate for nuclear as a climate solution, and then through that met Eric and have been working now with Eric for several years. On all kinds of interesting projects, including our co-founding a consulting firm called LucidCatalyst, where we produced many reports about, nuclear cost drivers and so on. And we decided to take it to the next level and found TerraPraxis, moving away from sort of more generic advocacy for nuclear energy as a climate solution towards actually designing strategies for nuclear technologies to be applied to really well-defined market opportunities, as well as designing the sort of delivery and deployment models that will enable the cost and speed and scale necessary for these technologies to become really useful in our climate efforts.
Okay. So you were anti-nuclear environmentalist before you started all this? Were you, protesting and the whole deal?
Afraid so, yeah.
Wow. Yeah. Well, no, it's good that you came around. What made you think about this? Was this your own research that allowed you to switch, or were you influenced by someone else?
Yeah, I was given a book we were given a book as a wedding present by my now husband's aunt, who is great friends with Professor Sir David Mackay, and so she gave us a copy of his book, Sustainable Energy Without the Hot Air. And I was reading this book, and I don't know if you know it, but he number crunches through what it would take to, at the time, achieve the sort of 80% carbon reductions for the UK using existing technology. And it became very quickly obvious that, it would be infeasible to, use the sort of extent of agricultural land and, the extent of infrastructure build if you were to try to get all the way to zero across our whole economy, not just electricity, but heat and transport and industry, just using renewables alone. So that was the sort of first eye-opening thing, and then I was really fortunate to be invited to work in the Department for Energy and Climate Change, working on nuclear policy at the same time as David joined the department as the chief scientist. So that's where I began my journey. Oh, well,
and now you're a leader in nuclear advocacy. So that's great to hear from someone who supports that.
I wouldn't have believed you at the time.
Oh, you're not alone. There are others. I spoke with Xeon Lights as well, who has followed a similar path.
Oh yeah.
In the UK.
Yeah, she's great.
Yeah. She's setting up new organizations all the time as well. So, Eric, your portfolio is very broad. Looking at your CV, renewables, energy storage, fossil, and nuclear. So, with this broad experience, you are now focusing on nuclear as well. What was your path to get here? Were you always pro-nuclear, or did you come from a anti-nuclear background as well?
I was an anti-nuclear weapons protester in college, and was arrested a number of times protesting, particularly the development of first strike capability during the 80s. And I think, I was sort of kind of a background anti-nuclear person. I sort of thought of that power applications as part of the military industrial complex. And
I think that's common.
Yeah. And was very interested in the sort of soft energy paths, appropriate energy type technologies, and became very knowledgeable about all that. I was recruited by an anti-nuclear group at one point in college to study up on nuclear reactors and be on some, radio shows and stuff, because I was good at understanding all the technical diagrams. But I never really I was never really involved in kind of the hardcore demonstrations against that. I just sort of, I think I had a view which is quite common among people who haven't really looked into this topic, which is that, there's some sort of large dangers, and we're not actually doing a very good job taking care of the whole nuclear fuel chain, and it's not a viable, scalable solution, and yada yada yada, all the kind of myths. And for me, there were really two things that started to happen. One was I started to be involved in a lot more large-scale energy modeling, looking at how are we going to actually convert our energy system from a climate perspective. I'm a little unusual in that I've been a climate activist since about 1986.
Wow. Before it was popular.
Before it was popular, yeah. And so I guess, I've gone through a lot of iterations about thinking the different ways that we could be thinking about solving that problem. And a lot of our work today at TerraPraxis and at LucidCatalyst involves looking at the the risks to the transition. So we spend a fair amount of time looking at solutions and what's scalable and what are the requirements for things that could be scalable and really meaningful in terms of rapid and sort of economically just transition. And also we look at what are the challenges that we're facing, not just with renewables, but including the challenges with renewables that we're facing. And are we really taking those risks into account? And so I've had kind of decades of looking at that as well. And I was involved in a very large scale startup as the CEO and as the chief technical officer for a compressed air energy storage technology. And we saw this as a way to integrate with wind farms and really produce kind of a primary energy source for the US that would, and Canada, that would be able to produce highly reliable power from these combined wind and energy storage projects. And we basically developed a vision for how to do this for the whole of North America. And that was my first example, the first kind of real experience of trying to take responsibility for solving the whole energy problem. And that was the thing that led me to get honored at the Obama White House and so forth. During the end of that company, we were basically crushed by low gas prices. When the fracking started and gas prices dropped from $8 to $2. All of our customers sort of went out of business and all of our projects disappeared. And that was a very kind of profound teaching about the risks of having a sort of one technology be the way that you're going to solve the problem. And during that time, I also got really interested in molten salt reactors and advanced nuclear, which some people describe as the kind of gateway drug to nuclear energy. So at that point, I began to explore very broadly the whole nuclear energy kind of solution set. And that has really led to the work that we do now on advanced deployment models and innovative applications for nuclear and the kind of the things that we're working on today.
That's interesting. So you've worked on the energy storage and renewables angle, and now you're coming around to doing nuclear. Can you give something of a balance? Like, do you feel that the energy storage renewables is a viable pathway, or do you think there's one that's better than the other, or what's your technical feel on which way we should be going to decarbonize our economy?
All the technology evangelists have a very rosy view of their technologies and almost completely ignore all the challenges to deployment. And to solve this problem, we can't just build a few plants. We can't just have a good year for installations for solar energy. We can't just sort of, yay, we built 10 gigawatts of wind. The scale of what's needed for this is so daunting that we need every single one of these clean technologies to be unbelievably successful, and then we might just make it. And we have to keep innovating because we don't have all the things. We're not commercially deploying all the things that we're going to need to solve this problem. So, we need to do lots of solar and batteries. We need to do lots of wind farms if we can. We need to figure out how to build lots of transmission if we can. Those things are all difficult, and they're all going to be gated by public acceptability and other challenges. And so we also need to repower all the coal plants with advanced nuclear heat sources and make highly deployable and low-cost synthetic fuels from nuclear energy projects to allow us to export clean fuels around the world. We need to do all of that. And we need to do it all at a scale and speed that we have not yet demonstrated in any of these technologies.
Yes, definitely. The scale of the problem is daunting, as you correctly point out. Now, TerraPraxis I've seen some reports on your website. You're talking about using nuclear to create hydrogen. and transferring, I've heard a lot of talk about hydrogen economy and how this is necessary. Can either of you give me a background on the case for hydrogen and the work that you've been doing looking at this?
Yeah. Well, what is interesting is that we actually don't really talk about nuclear at all. We talk about advanced heat sources, and we chose that kind of new label really intentionally in the report that we published last year, The Missing Link to a Livable Climate, because when we were distributing the early drafts of the report for peer review, we found that a lot of our peer reviewers were really getting stuck on the word nuclear. There's a lot of, very understandable preconceptions around cost and schedules, and a lot of the feedback we were getting was, well, wait, isn't nuclear too expensive and slow to make this contribution? Why don't, and actually what we're talking about is this entirely, first of all, really new technology. So high temperature heat sources that are coming to market, that are being commercialized this decade. So in the 2020s, we're going to see a lot of new products coming to the market that have really, that are unrecognizable from the kind of decades old gigawatt scale, traditionally constructed light water reactors operating today. Mm-hmm. Mm-hmm. And, we were trying to think of an analogy, and Eric, you were suggesting, it could be like a telephone. You think about a telephone from the last century, and what we think of as a phone today, a smartphone that is basically like a little computer in your hand that's incredibly multifunctional. That is an analogy for the kind of incredible paradigm shift that we're seeing in these new technologies coming to market. And if you combine that paradigm shift in the capability of these new technologies with really modern, high volume, high productivity manufacturing methods in world-class shipyards, which are, the sort of world's most modern and efficient and high productivity manufacturing environments in the world that are making really, really large, really complex machines already for the oil and gas sector, mm-hmm. Then you can actually completely change the paradigm, not only for the delivery of really low cost advanced heat sources at scale, but you can also apply those heat sources to new applications. And in particular, as you said, we really focused on hydrogen enabled synthetic fuels, because the combination of very low cost electricity with high temperature heat, a tiny environmental footprint, making them deployable on these kind of platforms that you might expect to see in the oil and gas sector today, with really high capacity factors, delivers super cheap hydrogen. I mean, it's the cheapest way to make hydrogen cleanly out of all of the options available to us, which we outline in our report.
Okay.
And the reason that we focused on the hydrogen, just the final thing to say, rather than the traditional power sector, is because when you look at all of the mainstream projections for energy consumption by mid-century, more than 50% of our energy is still coming from fossil fuels. And that is largely, because of, a few things, but, it's oil and gas are not going anywhere. They're really, these stubborn, hard to abate sectors of transport, heat, and industry are really tough to electrify, and therefore we need drop-in, clean substitute fuels that are comparable in terms of cost and performance with the oil and the fossil fuels that we're used to using today, if we're going to achieve the rapid switch within 29 years. It's funny hearing about Eric, working on climate 30 years ago. Here we are, right? We've emitted half of the emissions in the atmosphere today we've emitted in the last 30 years. We've got 30 more years. We've got 29 years, actually, to turn this around.
Yeah, I feel guilty about that.
Well, don't we all?
Me too.
And I guess, Al, I would just kind of amplify something that Kirsty mentioned now, which is that you asked the question about hydrogen, and what we're really talking about is using hydrogen as an intermediate feedstock in a process to make synthetic fuels.
Okay, this is
so
good.
We're not talking about the traditional view of the hydrogen economy, which is that everybody switches all the things to use hydrogen. We're talking about industrial production of hydrogen in a process that is using it right away to make a synthetic fuel, which is much closer to what we actually use today as an energy carrier. So either ammonia, which can be used in converted diesel engines and can be used for shipping and heavy truck transport and rail transport and all of these kind of very large-scale diesel engines, even power generation. It could be used in the place of LNG for gas turbines and so forth, and synthetic hydrocarbons, which are for the kind of more finicky applications like aviation fuel. And so we're really talking about making these products, and the hydrogen is just something that's going on inside the refinery or inside the FPSO to make that end product, which then enables us to decarbonize kind of our existing energy uses. So the problem that one of the big risks we see with the transition is that if you have to make everybody electrify everything, especially all the end uses, that's billions of consumer decisions that all have to go the right way, right? You can't have Al sitting in his house in Canada saying, well, I kind of like my gas heat, or I'm not really sure about this heat pump or whatever, right? I'm worried about what happens when it gets cold and my electric car doesn't run. Like, it doesn't matter whether those are rational concerns that people have. If they have those and those delay all those end use conversions, then we do not get decarbonization.
Okay, I like your thinking. That's good.
And so we feel like many of those things are good ideas. Like, I'm right now trying to evaluate redoing all the heating and cooling in my house with electric heat pumps. It's a great idea. It's not super easy to do. It's expensive. I'm sort of fortunate that I am in a place where I can think about doing that, but I sort of shudder to think that if the decarbonization effort depended on everybody going through this process that I'm going through, it's just not going to happen in time. And that's assuming everybody even wants to do it, right?
Yes.
And is prepared to pay for it, or able to pay for it, and that it's available to them.
It requires levers of carbon taxes and all sorts of things to make those decisions or force those decisions.
So this is why we feel like a parallel strategy, a complementary strategy, is to also decarbonize the things that people are using, so that if Al has a diesel car, he either gets an electric car and you've decarbonized the electricity system, so he's good, or you've decarbonized the diesel fuel supply with synthetic fuels, and so he's good. And either way, it works, right? And that's what we think is the lower risk way to approach this decarbonization challenge.
Because you're making it transparent to the consumer, basically.
Yes.
That their decision doesn't affect the decarbonization. It's decarbonizing at the source of the energy.
Exactly right.
And that applies at the industrial scale. It applies to developing countries, emerging economies. A drop-in substitute, a rapid switch using as much of the existing storage, distribution, transport, and end-use infrastructure as possible to create as little disruption as possible, as little additional cost. In fact, ideally, a lower cost would be really what would be needed. We use the analogy of the Impossible Burger, which is a plant-based meat substitute that is available in every Burger King now across the US, and it basically looks like a burger, it tastes like a burger, it costs the same as a burger. You buy it in the same, burger joint, and it doesn't really require any behavior change on the part of the consumer. It doesn't require anybody being willing to pay more. It makes the decision as easy as possible, and that's what we're trying to design here: Impossible Burgers for climate.
And for many people, the Impossible Burger actually tastes like what they want to eat. They're not making they're not saying, oh, I should eat less meat, so I'm going to sort of not enjoy my burger, right? They can, the whole sort of value proposition of that burger is that it tastes good, right?
Yeah.
I see.
It's substitute, not sacrifice. Yeah.
Yeah. So this is interesting. So I had, by scanning your documents, I had assumed you were supporting the hydrogen economy, the quote unquote hydrogen economy. And this is, a large talking point for people that are looking at the deep decarbonization is we have to switch all of our fuel processes over to hydrogen fuel. We need to transport hydrogen fuel in leaky containers around the world. We need to replace all of our motors with hydrogen burning fuel cells. And yeah, it's a daunting transfer that I couldn't see happening. So this gives me some hope, what you're speaking of, that this does seem much more feasible on the surface. I'd like to dig in a little bit more into the technical details of what process you've envisioned to get this carbon-free synthetic fuel and produce it at volume. I don't know. Is it a carbon-free process, or are you using electrolysis or methane as a feedstock to make hydrogen? What? Give me maybe a little bit more details in how you're doing this and what the real CO2 impact is of this process.
Sure. There's really kind of two models, and this could apply to other things as well, other chemicals and other fuel types. For example, our synthetic hydrocarbon route, we profiled the production of aviation fuel, what's called Jet A. That's one high-value product that there isn't currently another pathway to power the engines on jets for long-distance aviation. But you could, for example, apply the same pathway to making methanol if you wanted to use methanol in ships or other things. So the basic process steps are advanced heat source, advanced reactor, producing heat, running steam generators, which then provide steam to traditional steam turbine technology, generating electricity, and a little bypass steam going to the next step, which is high temperature electrolysis using solid oxide technology, which takes in steam and electricity as inputs, which makes hydrogen very efficiently, about 40% more hydrogen per kilowatt hour than a traditional low temperature electrolysis process.
This is the advantage of the high temperature over, say, the direct renewable source of electricity, which is the efficiency benefit you get from the high temperature steam.
Yep, and you also get very high capacity factors, as Kirsty pointed out, right? So you get to run the process as many hours as you can keep your reactor operating per year. You can be producing at full power output.
So you don't have the losses in ramping the heat up and down when the sun comes out.
Yeah, and so then that hydrogen goes into a reforming process, and for the synthetic hydrocarbons, we bring in calcium carbonate, which is limestone, and we run that through a calciner, and that produces CO2 and lime. This is a well understood industrial process. This is how we produce lime and ultimately how we produce cement, quicklime for cement and so forth. And then there are several ways to source sustainable CO2. This is just one that we looked at. And the CO2 is then run through a reforming process and turned into hydrocarbons by the addition of successive stages of hydrogen. So that strips it down to carbon monoxide, and then you run that through a Fischer-Tropsch process, and that makes your fuels. And there are a number of advanced reactors for that kind of process, including ones being demonstrated today that have a much more narrow spectrum of products that they produce. So you can tune them to not produce the waxes and various other things that come out of a Fischer-Tropsch reactor, but to have them just produce the product that you're interested in. And so we see a real potential to improve the selectivity of that process. And then the in the scenario that we developed, the lime that's produced from the calciner goes back into the feeder ship that brings the limestone out to the production platform. And on the way back, that's mixed with seawater and distributed in a kind of dilute solution back into the ocean, which then creates a process that absorbs about 1.7 times the CO2 that was produced in the calcining process. It gets turned into bicarbonate in the seawater and actually sequesters CO2, takes CO2 and carbonate out of the carbonate ions out of the seawater and fixes them into bicarbonate, which then sequesters that CO2 permanently. And this also has the effect of deacidifying the ocean. So the carbonate ions that are in the ocean today, which are increasingly plentiful due to the increasing partial pressure of CO2 in the atmosphere, are the reason that the ocean is becoming more acidic. And so this would not only sequester 1.7 times the CO2 that your jet fuel is going to produce when you burn it, but it would also be reducing ocean acidification in the areas where you were distributing this.
Wow.
So that's a vision for how to create and this would be very scalable. So the more fuel people bought, the more reduction in ocean acidification we would have, and we would actually be reducing net emissions by, because we're sequestering 1.7 times the CO2 for every molecule of CO2 that would be released when the fuel is burned. So, and this is a very important idea. I think one of the things that we're going to have to do in the future is design a lot of our processes to be carbon negative. Mm-hmm, mm-hmm. Right now, everybody sort of thinks, oh, can we get to carbon neutrality? That's what we need. But the system is going to be so messy, and there's going to be so much stuff kind of sneaking out of our carbon limits. And there are going to be so many countries in the world that are not really doing that great a job of clamping down on their carbon emissions, that we're going to have to figure out how to do really large-scale carbon negative things that are supported by our normal economy. So, can we make, so for example, one of the things we're looking at now with our Repowering Coal campaign, which is about repowering existing coal plants with advanced heat sources, with advanced reactors. So instead of burning coal, you have an advanced reactor, and that provides the heat for your steam generation. And so you basically get to reuse your power plant. You get to have your workers keep working there. The community gets to stay intact around that power plant, and you get to reuse the existing transmission. But there's an additional interesting wrinkle, which is for all of those plants that have cooling towers, there's a technology. You basically do something very similar to what I was describing with the lime and the calcium carbonate. You basically add lime to the water that's going to the cooling tower, and as it's releasing its heat to the air that comes through the cooling tower, it's also collecting all the CO2 from that air. Mm-hmm. So you can actually turn a repowered coal plant into a carbon negative plant. It can capture, so a 1 gigawatt coal plant can capture about 700,000 tons a year from the atmosphere.
Wow.
And at very, very low cost, because you already have the cooling tower, you already have the pumps. You don't need to be paying to add heat to the process because you're already rejecting heat through the cooling tower. That's what it's for. So you need to do some other processes to the water to get the CO2 out of that. And if you basically make hydrogen during that process, you end up with low-cost hydrogen and the lowest cost atmospheric carbon capture that we've seen to date. So this is an example of another thing where we need to really be designing scalable infrastructure that can be carbon negative, because we're going to need it all.
This is really good stuff. Very, very interesting, and I'm surprised it doesn't have a higher profile in the discussion about climate mitigation. Is this new? Is it like when?
This is very new. We're breaking it on the Alex.
Well, thank you very much, Alex. Thanks for the scoop, guys.
Yeah, sure.
No, this is very cool. So you have this idea, you have a process on paper. How far are you to testing it out, to demonstrating it? Is there a pathway, a timeline for you? Do you have a company in mind, or are you running a company that's going to do this? What's your pathway to actualization?
Well, as we sort of mentioned, we've done a lot of work on looking at what drives the costs of nuclear projects, and our Energy Technologies Institute Nuclear Cost Drivers Study is a kind of landmark report on nuclear costs. And we know that when you move from a sort of single project to a programmatic approach, and then from a project-based approach ultimately into a more product-based approach, you can step down your cost outcomes, to achieve really pretty compelling low costs and very compressed schedules. So we've spent years working on that, and we see a lot of potential with the advanced reactors that are coming to market this decade to be really manufactured products. But one of the big challenges that those developers have is getting a pipeline of orders that can support the upfront investment, the capital investment that's needed in the manufacturing facility, right? So they need a lot of customers to order their products, and then make that investment in manufacturing. And so one of the things that we've been interested in is like, well, what are the potential markets? And also what are the really, tough to solve problems? One of the, biggest challenges that we see in the decarbonisation agenda is the fact that we're still going to have 2 terawatts of coal operating by, mid-century. And if that existing coal fleet, or in the works, in the pipeline coal fleet, operates for its expected operating life, then that fleet alone will swallow up the remaining power sector carbon budget. So this is one of the big challenges that we face, and right now the plan is just shut down that coal. One of the major themes at the COP26 in Glasgow later this year, the big climate conference, is powering past coal. Mm-hmm. And when you think that more than half of that global fleet is on average about 14 years old, and is not only providing really reliable, useful electricity to support economies and societies, but also represents a lot of jobs and revenues into communities. We think that it's really unlikely, almost infeasible, that these coal plants will just be abandoned. And there's $1 trillion of investment that hasn't yet been recovered in that fleet as well. So we came to this, we started looking at the potential to repower coal plants, and, the technical feasibility for repowering coal plants with advanced heat sources is being pretty well established. There's a recent report by Stefan Kvist, which looks at Poland as a case study and a range of clean energy options to repower the Polish coal fleet. And he concludes that, advanced heat sources are a really good option. But, what we need is not to repower a single coal plant. We actually have to figure out how to do the whole fleet. So we're looking at a range of different advanced heat source developers, and figuring out a sort of standardized or generic building system design that these heat source vendors could all potentially supply into. And it's kind of largely informed actually by a study that we did last year for ARPA-E, looking at cost and performance requirements for advanced reactors, which was intended to inform upstream design decisions by developers to ensure that they're developing, really useful products that will have large markets. And one of the design configurations that we recommended was a separation of the nuclear island from the balance of plant via thermal energy storage. And that enables essentially the reactor to just run all the time at its, 95% plus capacity factor, mm-hmm. but either generate directly onto the grid or charge the battery, essentially, which is the thermal energy storage, and then discharge from the battery when electricity prices are high In other words, when the wind's not blowing, the sun's not shining, and that becomes a really flexible, really sort of complementary energy system that's very complementary to high penetrations of variable renewables in future electricity grids, and very economic for the plant itself. And so Bill Gates and the Natrium joint venture, TerraPower and GE Hitachi, yesterday they announced they're intending to build their reactor in Wyoming, which is, I believe, the US's largest coal producing state, on a retired coal site, which is really fantastic.
So that kind of plays right into your strategy.
Yeah. So what's really interesting is that if you take that separated nuclear island, and instead of attaching it to a conventional power island, you bolt it on to a former coal plant, you stop burning coal, you get rid of the coal boiler, and you have essentially a new source of steam. You can replace the heat source for the coal plant, keep a lot of those jobs, keep all of those other benefits, all without emissions.
Everything downstream from the burning section is the same.
Yeah, no more. It's the end of combustion.
Which also makes for a very low cost plant when you're done. So we believe that for a typical coal-fired station, the converted plant, including recovering the capital for the conversion project, will be, the cost of energy from that plant will be lower after the conversion than before.
Wow.
So you take a depreciated coal plant, which is not recovering any more capital, and you repower it with an advanced reactor, and you end up with a lower cost of energy afterwards. This is going to be transformative, because right now what happens is coal plants have relatively high fixed operating costs. A large amount of that is due to pollution control and fuel handling and fuel purchasing. And then when you reduce the runtime, if you have more and more periods of low priced power in the market, when solar is producing and setting the price, or when wind is producing and setting the price, coal plants tend to cycle down or cycle off during those times, and that reduces the capacity factor, which means that you have to recover your fixed costs over fewer hours, and so your cost of energy goes up. When you replace those processes with an advanced heat source, with an advanced reactor, you end up with a plant that has much lower marginal costs and will probably run all the time. And if not, the reactor will run all the time, and you'll use the thermal energy storage to cycle the plant up and down into the high-priced hours, which makes it, by the way, a very good complement to renewable energy being built. So it basically makes that plant into something that is an economically viable and climate viable complement to the renewables that might be built near that plant or in that power market. And that's really critical. The solution to making renewables reliable can't be burning lots of gas.
That's what's happening in New York. That's what's happening in Germany. That's happening everywhere that they shut down nuclear.
Yeah, it's the sort of not so hidden secret about the renewable intensive strategies is that they basically keep gas around for a really long time, possibly forever.
So you've basically invented a steam bypass, a valuable steam bypass for nuclear, advanced nuclear, that allows it to be load following to support renewable infrastructure and decarbonize the oceans and support internal combustion and deep decarbonization of thermal processes.
Yeah, I would agree with all that except for the invented part.
We're done.
I mean, yeah. Well, that's so. Yeah, now we just need to scale it up, Al. A lot of the work that we do, I mean, we've talked about sort of the technology and the concepts so far, but a lot of our work is also about business models and how to make things scalable from an investment perspective, how to fit them into the strategies of existing players, how to motivate players to move into these new spaces. And
well, that's the catalyst bit, and the praxis bit, which is the theory into action.
I can imagine a lot of people wanting to get on board this. So, my listeners are definitely pro nuclear, pro climate mitigation. How do we help? How do people get involved? Is there a grassroots movement here that people can help out with this, or is it?
We have on our website, we have a lot of publications, and a lot of these things are explained or laid out, and we've even tried to kind of get pictures produced to make these things kind of easy to communicate and to make them kind of concrete from a visualization perspective. And every community has opportunities to talk about these solutions and to begin to kind of broaden the discussion about the kind of solutions that we need in order to fully to solve the climate challenge in a sensible, feasible, and low risk way. And so I think familiarizing yourself with that thinking, that's the kind of first level of what we would offer. The second is that we really need to, there's a lot of renewables versus nuclear kind of chit chat that people engage in, both in the renewables community and in the nuclear community. And I think one of the things that really attracted me to working with Kirsty is that she has this very system level view that she promotes, which is that what we all want is the benefits of a clean energy system. And we need to achieve that system in the most cost effective, scalable, and low risk pathway. And to do that, and we don't know what that is today. Like when people present all these models that say, oh, we can do it this way or we can do it that way, those are all ideas. They usually are just focusing on the economics, and they're not focusing on all the feasibility questions that you were noticing and talking about earlier. So we have to all recognize that there's a lot of risk, and that this is like saving for retirement. You don't put it all in Tesla and say, I'm crossing my fingers and hoping that, that it's going to be work. You distribute it around. You anticipate that there might be currency changes, or that real estate might go up and down, or whatever. You think about it as a portfolio, and you try to have a high confidence strategy that you'll actually get to where you need to be at the time that you need it. And that's what we're not doing today as a community, as citizens. We're not demanding that there be kind of a level of feasibility, and that we think about what the risks are in our transition strategies, and that we come up with clever approaches to addressing those risks. And that's something that all citizens and all stakeholders and all people who care about this can do, is begin to get educated about that. We also have a webinar, Kirsty, in which we talk about the risks to the transition. And I would recommend that people, I forget, is that on our LucidCatalyst website, or is that on the TTI website? But that's really worth looking at too.
Okay, that sounds great. So we're getting to the end of our time slot here, and I really appreciate you folks coming on to give me this scoop that I'm going to now publicize to the world. Do you have any final comments you'd like to make to our listeners?
Yeah, I guess I would say that this is a very important decade that we're in. And the 20s are going to be the decade where we basically either set ourselves on a path to being able to fundamentally solve the climate problem, or where we don't. And where the direction that we're going now, where we focus only on one approach to solving the problem, which is renewable energy, is not enough. It's not that we shouldn't be building renewables. As I said earlier, we have to build huge amounts of all the clean energy sources. The problem is the insistence that that's the only thing we need to do. That is what is incredibly dangerous, and I would say even pernicious. And we need to expand the range of things that we're doing. We need to really understand what the risks are with these different pathways, and build additional pathways that don't have the same risks. And if we don't do that in this decade, it's going to be very grim in the future. And if we do it, this is what you've sort of begun to get a sense of today in this show is that we have scalable solutions that can really help solve this problem. And so this problem is resolvable. It's just that we need to reframe the way we're approaching this and include this broader range of solutions and really think hard about how those are going to be scaled up and deployed and financed and so forth. And if we do that this decade, we are setting ourselves up for success and for a prosperous and stable climate. And
part of that is going to be about creating the political mandate, and that's what everyone that's listening today can help do, which is really start having these conversations. Have these conversations with your friends and your colleagues, and write to your political representatives and demand this, because that's what will create the political mandate. That's what gives our politicians confidence to think differently, to act differently, and ultimately that is what will lead to investor confidence that will also be necessary to enable this change. So it's really profound and important. And Al, thank you for hosting us. To give us this chance to have this conversation with you.
Thank you.
And we're really pleased to be able to have been here and contributed. And thank you for your great contribution also.
Oh, thank you for coming on to the show. I really appreciate talking with you guys. It's been really interesting. And I can't wait to put this on the air and hear the feedback from our listeners. So great. Thank you so much.
Awesome.
Thank you.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/TheRationalView. Thanks for listening.